two common operations for running the Dijkstra's algorithm and the Bellman-Ford algorithm are the initialize single source and the relax operation. So let's see what these two operations do. Say we have a graph like this, a directed graph, and we are interested in finding the source path from this vertex S to all other vertices. So before we run either Dijkstra's algorithm or Bellman-Ford algorithm, we first assume that every node in this graph has two attributes. The first attribute is D and the second attribute is pi. What this attribute D is, it's an estimate of the shortest path, and this attribute pi is the parent node or predecessor attribute. Now before running either of these two algorithms, we first want to assume that the shortest path estimate for each of these vertices, so I maintain D and pi for each vertex, and we assume that, or we set the values of D and pi, all of them to infinite, t equals infinite, thinking that the maximum or the shortest distance between our starting node to all the nodes are very high. And then we also set all the predecessor nodes or predecessor attributes or the parent attributes to nil. We set that we don't have a parent for each of these vertices yet. This gives us a place to start all the algorithms. We also want to initially set the starting node have its estimate of the shortest path as 0, because the cost of going from the starting node to the starting node itself is 0. So this is done in this for loop. So for each vertex, all I'm doing is setting the D attribute to infinite and the pi attribute to null. And finally, I'm setting the D attribute for my starting node, starting vertex to 0. So this process simply takes my graph G, which is simply my vertices and edges, and then this is starting vertex S, and then performs these initializations to all the vertices in my graph. Next is the relax operation. So the relax operation takes two vertices U and V, and also all the set of possible weights. So this can be a weight matrix or just the weight between U and V. And what it does is relaxes this vertex V by considering the shortest path estimate of the vertex U. So say we have a part of the graph that looks like this, and say because of some operation we found out that the shortest path estimate to U is 5. And now we know that there is a path from U to V that costs 2. So this means that and also let's say that V already has a shortest path estimate of 9. This could be infinite, or this could be any value that is appropriate for V. Now that we have found the shortest path estimate of U to be 5, we know that if we take this path of 5 plus 2, then we can reach to V with a cost of 7. This process of looking at the shortest path estimate of a node that connects to my node V, from U to V, and updating the shortest path estimate for my node V by looking at the shortest path estimate of my previous node is what the relax operation does. So here 5 plus 2 is 7, so my V, shortest path estimate for V, updates from 9 to 7. Now what if V already has a really good shortest path estimate? So say we have a situation like this where we at some point ended up updating the shortest path estimate for U to be 5, and then we want to run the relax operation on UV with this weight 2. So here, since V already has a really good shortest path estimate, because 5 plus 2 is 7, so taking this path would actually make the cost of going to V higher. In this case, the relax operation doesn't do anything, so it keeps the shortest path estimate for V as it is. So this can be very easily written as, if the current shortest path estimate for V dot D, V is more than the shortest path estimate for U plus the cost of going from U to V, then we want to update the shortest path estimate for V, and we also want to update the predecessor attribute.